So, one of our clients manufactures microchips. Manufacturing microchips is a complex process that contains many steps and needs many different machines, processes, and systems, and builds the basis of a large and heterogeneous IT infrastructure. Responsible for manufacturing are process engineers who design and monitor the process. So the situation for a process engineer when we got hired was the following. Whenever there was a production problem during chip fabrication, a process engineer needed to consult the logs of many different systems. They had to manually log into equipment controllers, query databases, look at the message bus, look at the events, and so on. It was a tedious task and didn't often yield any useful results because it is quite hard to concatenate, to correlate this information sensibly. The client named the project Panaka after a figure of Greek mythology, the goddess of universal health. And that was the goal of the project, to universally heal the brokenness and the cumbersomeness of the current system. So now Panaka provides three main views of all the data in the factory with all the metrics that a process engineer might be interested in. Yeah. We have Kibana on top of Elasticsearch for log search and storage. We have Grafana for monitoring metrics on top of a Prometheus time series database. And we have a custom-made real-time alerting system we've dubbed Smart Alarms. We've achieved that by doing all the tedious work of collecting all the information that exists in the fab. So we tap the logs, we query the databases, we look at the message bus, and we bring everything together. And what we have in the center, where we're bringing all the data together, is our real-time stream processing system that is based on Riemann, a stream processing system that is written in Clojure and configurable and programmable in Clojure. Our system needs and supports many different kinds of input sources to achieve collecting all the interesting information. And our system outputs data in several formats for different applications. And we are very flexible with our approach to connect random other third-party software. So managing the inputs and the outputs is a lot of tedious and DevOps-style work, of course. This is the part that we have pushed out of our functional core in our functional software architecture. And in our functional core, we take care of the interesting and the nice parts. So that is like filtering of events, transformation and enrichment of events, accumulating information, combining events from all kinds of different input sources, correlating the information, doing data aggregation and projections. To do that, we've developed a domain-specific language that can identify the events, destructure the events to access the data in them, and do something with the event data. We implement the domain-specific language as a monad that allows us to express the domain logic in a specialized and in a concise way. And here's how that looks like. So on the top, there is an example event that we have here. The format is like represented as a nested Clojure map. And at the bottom, you can see a small example of how the matching, the fields, and then the processing of the matched event works. So it's a concise pattern matching, and only if the event matches, we process another event, we process an alarm. And the domain-specific language is easy and clear enough for even the process engineers, the domain expert, to use by themselves to develop their own filters and rules. And the system is a huge success. This is a direct quote from one of the process engineers. So the process engineers, they fear a so-called daily delivery meeting. It sounds innocent, but producing microchips is high stakes and an expensive endeavor. It burns a lot of money. And with the system, the process engineers are able to catch the problems before the managers even get notified about it, before the managers even realize. And this is quite a testimonial for the successful project for domain-specific languages and for functional programming in the real world. And I am Marcus, and I'm out of time now. Thank you.
Thank you, Marcus.